Hello, everybody. Learning is a hobby here. In this video, I'm going to go through the exercise set for section 5.3 in Tao's Analysis 1 book. So let me bring up my solutions and we'll go through them. There's not that many problems here, more than the previous two sections, but not very much at all. So let's just get through them. Okay, so we'll start with the first question here, 5.3.1. Tao asks us to prove proposition 5.3.3. Let me remind you of what that theorem says. Just scroll up here in the notes for this summary of section 5.3. So proposition 5.3.3 is the proposition that tells us that formal limits are well defined. In other words, we have to show that it's equivalence of real numbers is an equivalence relation. So it has to be reflexive, symmetric, and transitive. So let's go and do that. He does give a hint here. He says you may find proposition 4.3.7 useful. Let me remind you of what that theorem is. That's this one here from chapter 4. Where we have all these properties of rational numbers being epsilon close. So we'll use these in a couple of the problems here in this section. Okay, so let's show that equivalence of real numbers is symmetric. Sorry, it's reflexive first. So let an be a Cauchy sequence. Then if x equals the formal limit of the ans is a real number. Clearly an and an are equivalent Cauchy sequences because they're the same sequence, right? For any epsilon greater than 0, the distance between an and an is 0, which is always less than or equal to any epsilon. For all n greater than or equal to 1, therefore x equals x. Right, then we show symmetry next. Let x equal the formal limit of an and y equal the formal limit of bn for Cauchy sequences an and bn. Assume x equals y, then an and bn are equivalent Cauchy sequences, which implies that an and bn are eventually epsilon close for all epsilon greater than 0. So an bn are epsilon close for all n greater than or equal to capital N for some capital N in the natural numbers for any epsilon greater than 0. Then bn and an are epsilon close for all n greater than or equal to capital N by proposition 4.3.7 part B. That's this one here. I'll just remind you of it. So part B says this: let epsilon greater than 0. If x is epsilon close to y, then y is epsilon close to x. So by that part of theorem 4.3.7, bn and an are eventually epsilon close for all epsilon greater than 0, which implies that bn and an are equivalent Cauchy sequences, which means y equals x. So symmetry is satisfied. And lastly, we have to show transitivity also works. So here in part 3, we'll let x equal y, y equals z, and then we want to show that that implies that x equals z. So let x equal the formal limit of an, y equal the formal limit of bn, and z equal the formal limit of cn. Then an and bn are equivalent Cauchy sequences by definition, and definition of equality. And bn and cn are equivalent Cauchy sequences. Then there are n and prime in the natural numbers, capital N prime in the natural numbers, such that for any epsilon greater than 0, n greater than or equal to capital N implies the distance between an and bn is less than or equal to epsilon over 2, and for any n greater than or equal to n prime, the distance between bn and cn is less than or equal to epsilon over 2. Then for each n greater than or equal to the max of capital N prime, the distance between an and cn is less than or equal to epsilon over 2 plus epsilon over 2, which is equal to epsilon by proposition 4.3.7 part C. Let me just remind you what that says. That's this part here. Let epsilon delta greater than 0. If x is epsilon close to y and y is delta close to z, then x and z are epsilon plus delta close. Okay, therefore, for any epsilon greater than 0, an and cn are eventually epsilon close, which means that an and cn are equivalent Cauchy sequences, which means x equals z. All right, so that's 5.3.1. So that's the proof of that lemma. What was it? 5.3.3. Yeah. Okay, next problem, 5.3.2. Tao asks us to prove lemma 5.3.10. And again, he gives a hint that 4.3.7 may be useful. Let me just remind you of what 5.3.10 says. So going back to the summary for the section. Okay, that's this proposition here. Multiplication is well defined. So there's two parts to this. We want to show first that xy, so if x is the formal limit of an, y is formal limit of bn, and x prime is the formal limit of an prime, then xy is also a real number. So that's the first thing we have to show. And then furthermore, we have to show that multiplication satisfies the axiom of substitution. So if x equals x prime, then xy equals x prime y. So we'll do that in 2 steps. All right, first let's show that xy is a real number. So let x, y, and z be defined as in the lemma. Then an and bn are Cauchy. Then there are capital M prime greater than or equal to 0, such that absolute value an less than or equal to m, and absolute value bn less than or equal to m prime. That's because Cauchy sequences are bounded. If you remember, we proved that a while back. For all n greater than or equal to 1. Also, for any epsilon greater than 0, there are capital N prime in the natural numbers, such that in absolute value aj minus ak is less than or equal to epsilon over 2m prime plus 1, and absolute value bj minus bk less than or equal epsilon over 2 times capital M plus 1 for all n greater than or equal to capital N, and all n greater than or equal to capital N prime, respectively. Then for any epsilon greater than 0, there is n squiggle, or n tilde, I guess, if you want to call it n tilde, equals max n prime, such that for all jk greater than n tilde, greater than or equal to n tilde, the absolute value of aj minus ak bk is equal to absolute value aj bj minus aj bk plus aj bk minus ak bk, which is less than or equal to absolute value aj times absolute value bj minus bk plus absolute value bk times absolute value aj minus ak. That follows from the properties of absolute value that we went over in chapter 4. Actually, was it chapter 4? When did we go over the properties of absolute value? Whenever it was, I'm not going to go back in the notes. Okay, so that follows from that, and then that's less than or equal to capital M prime epsilon over 2 times M prime plus 1 plus capital M epsilon over 2 times capital M plus 1. And obviously that's less than or equal to epsilon over 2 plus epsilon over 2, which is equal to epsilon. Therefore, the sequence of a and bn's is eventually epsilon steady for all epsilon greater than 0, which implies that the product sequence here is also Cauchy, which implies that xy is the limit of an times the limit of bn equals limit an bn is a real number. All right, so that's the first part. Second part now is we have to show that multiplication of real numbers is well defined. Okay, so if x equals x prime, then an and an prime are equivalent Cauchy sequences, which implies that they're eventually epsilon close for any epsilon greater than 0. Similarly, bn is eventually epsilon close to itself for every epsilon greater than 0. Also, an, bn, an prime are bounded by some non-negative rationals m prime, m double prime. Again, that's because they're Cauchy sequences. Let m tilde equal the maximum of m prime, m double prime, or epsilon. Then for some capital N prime, capital N double prime in the natural numbers, an and bn, the sequence of an's, the sequence of bn's, sequence of an primes are eventually epsilon over 3 m tilde plus 1 steady. Then for any n greater than the maximum n prime, n double prime, the distance between an bn and an prime bn an bn minus an prime bn is less than or equal to epsilon m tilde over 3 m tilde plus 1 plus epsilon m tilde over 3 times m tilde plus 1 plus epsilon squared, but epsilon is also less than m tilde, so that whole sum there is less than or equal to 3 epsilon m tilde over 3 m tilde plus 1, which is less than or equal to epsilon by proposition 437H. I'll show you that in a second. Therefore, the two sequences are equivalent because they're eventually epsilon close. So xy equals x prime y. Let me just show you for proposition 4.3.7.h, which is what I used here to show that. So part H of 4.3.7 says this: let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then xz and yw are epsilon absolute value z plus delta absolute value x plus epsilon delta close. And that's what I use to show this this step over here. Okay, and that proves that the product of two real numbers is a real number, and also that with our definition, and also that the product of real numbers is well defined. Okay, next problem, 5.3.3. Let A, B be rational numbers. Show that A equals B if and only if limit A equals limit B. This allows us to embed the rational numbers inside the real numbers in a well-defined manner. And again, in the section summary, tau refers to, or in the section itself, tau refers to, proving this statement in the exercise set. So that's what I'll do here. So here's the proof. Let A, B be rational numbers such that A equals B, then A minus B is equal to 0, which implies that the sequence of A's and the sequence of B's are eventually epsilon steady for all epsilon greater than 0, which implies that the sequence of A's and the sequence of B's are equivalent Cauchy sequences, which means that limit A equals limit B. Right, and then we have to show the other direction because this is a biconditional statement. Next, let lim A equal lim B, then the sequence of A's and the sequence of B's are eventually epsilon close for all epsilon greater than 0. Then for any epsilon greater than 0, there's a capital N in the natural numbers such that for all n greater than or equal to capital N, the absolute value of A minus B less than equal epsilon. Then that means the absolute value of A minus B is equal to 0 by trichotomy of the rational numbers. Therefore, A minus B is 0, which means A equals B. All right, and that's the proof of that. Next, 5.3.4, let AN be a sequence of rational numbers, which is bounded. Let BN be another sequence of rational numbers, which is equivalent to AN. Show that the sequence of BNs is also bounded. He gives a hint here. He says use exercise 5.2.2. Let me just show you what that says real quick, and then we'll get to my proof. All right, exercise 5.2.2 says this: let epsilon greater than 0 show that if the sequence of ANs and the sequence of BNs are eventually epsilon close, then the sequence of ANs is bounded if and only if the sequence of BNs is bounded. All right, so we'll use that to prove this. Okay, let AN and BN be equivalent sequences, and let the sequence of ANs be bounded. Since AN and B, the sequence AN and the sequence BN are equivalent, they are eventually epsilon close for all epsilon greater than 0. Therefore, by exercise 5.2.2, BN is bounded since AN is bounded. And that's basically it. Okay, and last problem in this problem set, 5.3.5, Tau asks us to show that the formal limit of the sequence 1 over n is equal to 0. So here's my proof. For any rational epsilon greater than 0, 1 over epsilon is also a rational number because epsilon is bound not equal to 0. So and 1 over epsilon also ends up being positive as well. Also, there is some capital N in the natural numbers such that 1 over epsilon is less than capital N by proposition 4.4.1. Then by and I'm not going to bring that one up because I didn't bring up my summary for 4.4 section 4.4, but you can look back in that video. Then for any n greater than or equal to capital N, 1 over epsilon less than n less than equal little n implies 1 over n is less than or equal to epsilon. Therefore, for any epsilon greater than 0 and any n greater than or equal to capital N, the distance between 1 over n and 0 is 1 over n, which is less than or equal to epsilon, which implies that the sequence 1 over n and the constant sequence 0 are eventually epsilon close for every epsilon greater than 0, which means that the formal limit of 1 over n is equal to the formal limit of the sequence of zeros. Is equal to the real number 0. And that's it. That's the last problem in this section. So, okay, so that's section 5.3 out of the way. Now there's still 3 more sections. I put 3 or 4 more sections left in chapter 5. I think it's 3 more. But the next section deals with the order relation on the real numbers. So we'll look at that in the next video. My next video will be the summary of section 5.4, and then we'll do the exercise set. The exercise set for 5.4 is kind of long, but I'll probably be able to get through those 2 things at least this week. So look out for those videos. And the last two sections I think are not that long. So once we get past section 5.4, we should be smooth sailing. And then when we finish chapter 5, as I've mentioned a bunch of times already, then we'll move on to the epilogue for Spivak and do his construction of the real numbers. And then we can get to the derivative section, derivatives and integrals in Spivak. So anyway, I was hoping to get through all this stuff before the end of the summer, but we will be done with it relatively soon. So a little bit late, but not too much past when I was hoping to finish. But anyway, I'll see you guys in the next one. Let me know what you think down below. Give me a like and subscribe, etc., etc. And I'll see you guys in the next one.